I think this we went through. Okay. So we saw this in the last class where we said we need to analyze and use the analysis input into the design, and that way we will be able to come up with a good, efficient algorithm. Now, what do we mean by analysis of algorithms, right? Basically, it is telling when you run this algorithm, how much time it is going to take. This is the most important focus when we say analysis. So, and every time we want to measure something, we need a metric, right? Like when you want to measure a distance, you use kilometers. So when you measure the performance of an algorithm, you need a metric. And the metric that we are going to use is big O. So sometimes it is also called as big O. This is the pronunciation, and the symbol is the capital O. The capital O is called the big O. Okay. Okay. So when we analyze an algorithm, right? We saw an example of search, right? We saw an example of linear search in the last class. So we said, okay, I want to search a person in the class. So how do I do? I go one by one, and that is exactly what a linear search is. Now, if I have, say, 5 elements or say, let's take your class, say your class is what, a strength of 13 students. So I want to search one person in your class out of 13 students. Probably I will take some time. I will take some X time. Okay. But I say I need to search, apply the same methodology and search for 100 students. I'm going to take more time, right? So similarly, as the input increases, my time of computation is going to increase. Right. So, this is what exactly we are going to analyze. And this way of analysis is called asymptotic analysis. So when we say asymptotic analysis, that means we are only concerned about the change of input. And we are saying that all other aspects, all other factors, we are not even considering. We are saying that they'll always be constant. So we are only focusing on the change in the input and how is it going to affect the time it takes. So the primary focus of our analysis of algorithms will be based on the input. Okay. So we understood that as the input of the algorithm changes or increases, the time that takes to compute also increases, right? However, there are some conditions, there could be a certain way, a certain methodology in an algorithm where no matter how much you change the input, the time never changes. It's always fixed. So you could have a case where it's always constant time. Okay. So you could have cases where you could have an algorithm which behaves always in the constant time. Say, suppose it takes 2 seconds to execute. No matter your input is 13 or 100 or 1000, it doesn't matter. It always takes, say, 2 seconds to execute. So you could have cases where you always have a fixed constant time, or you could have a variable time where it changes as your input changes. So this primarily the focus on changing in the input and how your algorithm behaves is called asymptotic analysis. Clear? Clear? Any doubts? Any doubts? I can't hear you guys. Or show me some action. Clear?
Ma'am, can you please explain once again?
Okay. So when we analyze an algorithm, okay, like we said, if you take a simple searching example, now in your class of say 13 students, if I need to search one student, and if I go in a certain order, I start with student number 1, whoever is sitting in the front, I go one by one and I ask, is it you? Is it you? So that methodology, if I take, probably it will take some 10 minutes for me to figure out the person whom I'm looking for. Right. However, if the class strength is say of 100 students, I'm going to take a more number of time. I'll probably take 20 minutes to figure out that person, right? So as the input increases, right, as the input increases, the time computation also increases. You can see this graph, right? It's going up. The time is taking more. So this analysis of how the input changes when your time changes is called asymptotic analysis. Okay. Like I said, I'm going to share all of this. I'm going to share the definitions and material. So I suggest if you can focus, just absorb the concepts. And if you have any doubt, let's engage in this session. So that way, I think you'll be more focused. All right. Okay. Now, why do we have to analyze this runtime measurement, right? Like this is important because, say, suppose we have you all have a lot of apps installed in your phone, right? Now, suppose you have an app where to open itself it takes say 1 minute, and any operation, any click you do, it's responding so slowly. What are you going to do with that app? You're immediately going to delete it, right? You probably install it, and within few usage, you're going to dump it off. That is why it is very important that no matter, but the logic is perfectly written fine. It does what it does, but it's going to take more time to do what it does. That's not acceptable. I mean, at least in today's world, any app which is any application, whether it be your phone app or whether it be your business applications, if they perform slow, they're going to literally dump it off and pick up another solution and move it on. So that is why analyzing the runtime complexity and writing a better design is really, really important. Okay. What is the other advantage of doing this? The other one is, suppose you have an alternate way of doing, like you have two different algorithms, right? How do you decide which one to pick? So that also helps. So suppose you do this analysis and you say that this algorithm is taking more time, so I'm not going to use this. And this algorithm is taking less time for me, so I'm going to pick this one. So this is good. So to do that comparison between different design logics and pick the right one, your analysis also comes into picture. Okay. So we said, so you all understood what is analysis, okay, and why we need to analyze algorithms. And we also said that we need everything you measure need a metric. So in our analysis, we're going to use big O as our metric. Okay. Now, I'll give you an example before getting into what big O does. Okay. Suppose you want to purchase a car. Okay. You go read up his descriptions, and you will always see that for any vehicle, right, the manufacturer would have told this vehicle will perform at so and so speed. Say this performs at 50 kilometers per hour. This is the performance of this car. But what they are actually quoting, any confusion? Okay. Yeah. So what they're actually quoting is actually the best case. It doesn't mean that your car always performs at 50 kilometers per hour. Right, because this is the test what they would have done on all the best roads, right, in the best possible way, empty traffic, no traffic, and very good roads. Your car would give say 50 kilometers per hour speed. But if you come to a bumpy road, right, it doesn't give 50 kilometers, right, and nobody promises that. Say your car would come down, your performance would come down to say only 20 kilometers per hour, right? And say you have, okay, the roads are good. You're driving in a city roads, but the traffic is bad. So you're always like going and stopping, going and stopping, going and stopping. That is also going to decrease your performance. So on an average, where roads are good, but traffic is bad, it may come to say 30 kilometers per hour, right? And only in the best case, is going to give 50. Right? This we understand, like nobody will go question the manufacturer that, no, you said 50, I'm not getting 50, right? Nobody questions that, because we all understand that when they say performance, it is measured in 3 different measures, right? The best case, the worst case, and the average case. Now, same thing is with the big O, right? So when we measure any algorithm, we always will find what is the best case performance of the algorithm, what is the worst case performance of the algorithm, and what is the average. So we'll always get these 3 numbers. Okay. So big O, we will have the best, average, and the worst case. We'll start relating these points. Just keep these concepts in your head. Terminologies are new to you. Just keep them. And as we go ahead with the class, you will be able to connect those dots. So you know what is big O? You know that it's a metric of measuring performance, and it's going to have three values. It will have a best case, worst case, and average case value. Now let us take an example and see how do you measure it actually. This is the same example which, because you're familiar, we discussed this in the last class. I'm taking the same thing. We are talking about linear search, right? So what happens in a linear search? Say suppose you have, okay. Say suppose I'm having an element of 5. So that means my, let's see if this works. Okay. So I have 5 number of elements. Like for example, I have 1, 2, 3, 4, 5. So I have 5 elements and I want to search something. So say example, I want to search 20. So how are we going to do that? We will start one by one. So first we will inspect the first element. And in this case, it so happened that I got the first element right? So how many times did I search in this case? Only one time. So I just went to the first candidate. You can pick it as students. Okay, I went to the first student and right away, that was the student I was looking for. So I just have to do it one time. Now let us look at a different scenario. Same input, okay? I'm not changing the input. It's the same input, but I want to find 40. Okay, so how am I going to do? I go to 20, I say no. I go to 15, I say no. Then 9, I look at 8, and finally I got what I wanted, right? So how many times now did I search? 5 times. So after 5 times, I got what I wanted. Now let us take another example. Okay, input is the same. Now I want to search 9, right? So I go to the first element, then second and third. At a third element, I found it. So in this case, I searched 3 times, right? So you see that the method of searching is the same. I'm going one after another. However, the efficiency is changing. Like maybe, yeah, here I've summarized, right? So we saw the case where in the first attempt itself, I got what I wanted. We also saw the case where it was the last element. It was the last element that I wanted, and I had to go look up every element in that list. So that was my worst case. And we also saw the case where somewhere in between I got it. I didn't have to completely go over all the elements, right? So this was one example where we witnessed that the same linear search algorithm can behave in the best case, right? It can behave as an average case. It can behave as the worst case. Is this clear? Is this clear? Good. Okay, now this is based on the sample of 5 elements, right? We understood that in this case, best is 1, say average is 3, and the worst is 5. But we want to generalize this because our input, we don't know. It could be 5 elements, 10 elements, 20 elements, right? So how do you generalize that? So here, it is the best case is always going to be the first element. So I put it as big O of 1. So now you're seeing how we represent this big O, right? The best case, we're going to say big O of 1. Now, the worst case, I'm putting big O of n. So what does n mean here? Can everybody tell me?
Number of elements.
Perfect. Yes. So here it is. Number of elements. Like you saw here, it was 5 and this is 5. So basically in our case, the worst case is same as number of elements. So that is why we are going to put big O of n as the worst case. And then the average could be half of it. Like on an average, I may find somewhere in middle of it, right? So that is why we say the average of this is n by 2, big O of n by 2. We're going to apply this. So we spoke of big O, right? But big O is not just the only measurement unit we have. Like for example, I said if you want to measure a distance, you will take kilometers, but kilometers is not the only unit, right? You can measure it in millimeters, centimeters, you can measure it in meters, kilometers, right? So similarly, the performance, the runtime complexity of an algorithm can be measured in different ways. Big O, omega, theta, little o, and little omega. These are the 5 generally. There are many more, but I think from our academic point of view, these 5 are good for us to know. But this is where we are going to use this and apply to all our algorithms. Like any algorithm we do, we will be computing the big O only. We will not be focusing much on the other types, but you need to know what this is. Okay, we'll quickly see the definitions of this. Big O. So what does big O mean? When I say the algorithm is say big O of n, what does that mean? What I'm saying is the algorithm will be at least better or equal to the worst case, right? Now, if I have to write a linear search algorithm, I should not make it worse than big O of n. We know that linear search algorithm, what was the worst case? Big O of n, right? I should not write it such that it goes beyond big O of n, right? I have only 5 elements, but I'm say iterating 2 times. Say I'm iterating going over double the time and then finding out this is wrong, right? So we know that we can do it efficiently. Like there are ways where I can do the search even lesser than n. Okay, that your algorithm can do that. It can, that's very good. You can do lesser than the worst case, but at least match the worst case of the algorithm. It should not go below the worst case. That is what Big O says. And this is why Big O is, I will go through everything and then we'll come back and see why Big O is more important than other ways of measurement. Okay. This is just a formula. I think if you understand one, the rest will follow the same. If you want to put it in a formula and explain what a Big O is, it says a function is equal to the big O of g of a function f of n is equal to big O of a function g of n. So what is n here? N is a positive number, and assume that there is a constant called c. So how do you represent in a formula? The function f of n should be lesser than or equal to the constant of g of n. So why have we put constant here? Because our input will change, right? So that we don't know. So we place a constant and we say whatever function we write is at least going to be in the performance less than or equal to this some constant of g of n. Okay. This is the representation. I think you go through this 2-3 times, you'll get more familiar with this. But more than the formula, I want you to understand the concept, right? When we say big O, you need to say that my algorithm will be at least better or equal to the worst case of that. It's not going to go worse than the worst case, right? Okay, what is omega? Omega is the best case. You are comparing against the best case. Okay, that's the only difference. So you're saying that you can write an, suppose in the linear search, I mean, just for explanation purposes, I'll take this. We know that linear search, we got it in the first shot, right? This is a bad example, but keep it this way, okay? Now, what I'm saying is I can write an algorithm which can be better. It can solve it with, okay, let's say my best case was big O of n, okay? Best case of some algorithm was big O of n, okay? I can write an algorithm which takes lesser than the best case, okay? But at least it should match the best case. It should not go below the best case. Like for example, I say my algorithm takes 5 seconds to run, okay? This is the best case, okay? Now I'm what if I'm going to measure as theta of omega of the algorithm, I'm going to say that omega of this algorithm will be lesser than or equal to 5. It's not going to go below the 5 mark. One second. Okay. I'll just correct myself. So what theta says is it should at least match the best case. So it says I can write an algorithm which should at least match 5 seconds, and then it can go either 5 or 6 or 7, right? Anything more than this, but it should, the best case should be at least 5. So that's what it says. My algorithm, I'll write it such that it can take more time, but it should not go below. It should be at least my best case. Any confusion here? Okay, let me ask, I'll go through this and then I'll ask you some questions. So I'll know if you understood. Okay, theta is like in the middle. I say my best case is 5 seconds. Okay, my worst case is 50 seconds. So I can write an algorithm which is between this. It can be 5, it can be more than 5, anything up till 50. It cannot go, if I go between 51 seconds, this is wrong. If I go less than 4, 5, 3, this is also wrong. So my computation, my algorithm can lie between the best case and the worst case. So that's what this says. So runtime of an algorithm is greater than or equal to the best time or less than or equal to the worst time. It's lying in between. Okay. Let me ask you a question. Okay. Say I say that my algorithm okay. Let me say my algorithm, the best case is going to take 1 minute. And the worst case, it's going to take 1 hour. Okay. If I want to say that my algorithm, the big O is say 50, big O of my algorithm. Okay, say I'll put it as big O of G of N. Okay. Big O of my algorithm is 30 minutes. Is this satisfying or is this wrong? Okay, anybody just volunteer and tell me when we say big O, did we say that it is less than or equal to or greater than or equal to best case, worst case? What did we say? You can just give it to me. It should be correct. It should be less than or equal to worst case, correct. So in this case, is it satisfying? Is it less than or equal to the worst case? Yes. Okay. Now, let me say, I'm saying my omega, omega of my function that I've written, that is my algorithm, is taking 30 minutes. Okay. Is this correct? What is the definition of omega? What should it do? Equal to?
Best case.
Best case. So is this satisfying?
Yes.
Yeah. Okay. Now, same thing. If I say theta of my function g of n is 30 minutes, same 30 minutes. So what is the definition of theta? It should be greater than or equal to best case. And it should be less than or equal to worst case. So that means it should lie between my best case and worst case. Is it lying between best case and worst case? Yes, no? Yeah. Okay. Now, if I say big O is 2 hours, is this correct? Is my algorithm meeting the requirement or not? No. If I say theta of say 5 hours, is it meeting the requirement or not? Sorry, omega of 5 hours. Is it meeting the requirement or not?
No, ma'am.
Okay, what is omega?
Yes, ma'am. Yes, ma'am.
Yes or no?
Yes, ma'am.
Yeah. Okay. Okay. And I say theta of 5 hours. Is it meeting?
No, ma'am.
Okay. Now I will tell you why big O only we use. Like big O is the most widely used. See here, we said, okay, best case is 1 minute. Worst case is 1 hour. Okay. most of the times when you run the algorithm, right, you will come across scenarios where it's going to be the worst case. I mean, best case will be very minimal circumstances. Most of the times, you will have so many factors, the input and other things, which will fall into the category or near to the category of worst case. So that is why it's very important for us to measure our performance not against the best case, against the worst case. Okay. Now, what is the problem with the other two? Right here, it is very clear. The moment I go beyond my worst case, I know that this is wrong. Right. The problem with omega is even if I go beyond my worst case, it doesn't care. All it is saying is do better than the best, and I'm okay. You take 1 minute, you take 2 minutes, or you take 10 hours. It says okay. So that is why we don't prefer this, because most of the times, right, we need to find the worst case and compare it against it. Theta is same as pretty much same as omega. Here again, right, we are seeing the boundaries of best case and worst case. Like I said, most of the times best case will happen. It is only that worst case that we are supposed to focus on. So that is why we prefer big O. This notation is what we prefer. Can anybody re-summarize? If I ask you, we have these many different metrics, right? We have big O, we have omega, we have theta. Why is that most of the analysis use big O? Can anybody answer? Give it a shot. You can look at this example, what is happening here, and just tell it in your own words. Come on, try it. Why is there so much silence in the class? You did not understand? You all gave the answers, right? I assume you understood. Any doubts here? No. Then I'm just asking you to re-summarize what you understood in your own words. Why is it that we have different ways of measuring, but why is it that we prefer big O? Look at this example. This has crossed our worst case, and we know that this is wrong. Whereas here we have crossed our worst case, but still we say this is okay.